So we're ready to launch Chapter 6, and we'll be dealing with differential equations and how they relate to modeling real life situations mathematically. Specifically today we're going to focus on the idea of the antiderivative. Differential equations have different kinds of solutions. They have what's called a general solution, and then they have what's called a particular solution. The general solution is always with a plus c, and the particular solution you have to solve for that c value given an initial condition. So remember that we define capital F as the antiderivative of a function. Therefore, f prime would take you to regular f. And then when we integrate that capital F is always accompanied by the plus c, called that constant of integration. Some of the properties of integration is that if you have a k constant here, you can pull it out to the front, and k can sit in front of an integral. We also can add and subtract integrals separately to each other. We cannot multiply and we cannot divide. Only addition and subtraction are defined for integrals. I wanted to point out that the way this problem is written is technically incorrect. There should be parentheses included before the 2x and after the cos x. Okay, without those, it looks like the integral only applies to the 2x and the dx is only attached. Okay, so it would be incorrect to write that without. So let's put the parentheses in to correct that. And then we're going to find the antiderivative of each term. So 2x has an antiderivative of x squared. Negative cosine has an antiderivative of positive sine of x. And this is an indefinite integral, so we have to have the plus c. So that was an example of working with the power function. When you have a power, you raise the power by 1 and then divide by the new power, as long as n was not equal to -1. Because when n is equal to -1, then the new power would be 0, and you can't divide by 0. So what do you do when n is equal to -1? Well, that's the situation here. And when n is equal to -1, you can't use the power function. You have to write it as a fraction, and then antiderivative using the natural log definition. Okay, the natural log is defined with those absolute values. Okay, that's part of the requirement, and then plus c. Trig functions are all defined with an antiderivative as well. Okay, so just a reminder about where the negatives show up in the antiderivatives. So you have to have the specific form, so secant u tan u, and then that would go to secant u, or cosecant squared. And this is just really memorizing the antiderivatives of trig functions backwards. We've already memorized the derivatives, so we're just going to go backwards to the antiderivatives. Exponential functions, okay, e to the u, its antiderivative would be e to the u divided by the natural log of e and followed by u prime plus c. A to the u would be a to the u divided by the natural log of a and u prime plus c. The natural log of u does not have a derivative that is memorizable. Okay, does not have a distinct derivative. We need a different technique to deal with the natural log of u, which we'll cover at the end of Chapter 6, but it is not a defined antiderivative. So we'll just put maybe not yet. The reciprocal functions, so these are the 1 over functions. The natural log function is one of the most commonly, we've talked about that already, with the absolute value plus c. A lot of people try mistakenly to apply this to other rules. So like they'll see a square here, and so then they'll just throw a square right there. Okay, that is a fake math. That is not the antiderivative. You would use the power rule if you had a square. Only the powers of -1 lead to the natural log as its antiderivative. The other three are all inverse trig functions, so this would be either inverse sine of u or inverse cosine of u plus c, depending on whether it was a positive or negative. Okay, then we have inverse tangent of u or the inverse cotangent, again depending on if it was plus or minus, and then finally the inverse secant or the inverse cosecant of u. So those are defined formulas. If the format fits, if the shoe fits, okay, if the format is right, then you've got your defined antiderivative. So solving these differential equations where you have one equation relating a derivative to another, this is a differential equation, our strategy is always separate followed by integration. So separate and integrate. Always the strategy for solving a differential equation. So if we're going to solve the following differential equation, our first step has to be to separate. And by separating, that means putting the right side in parentheses and tacking on the dx. Okay, that's the separation of variables. Then you can integrate both sides. So y would be equal to, and this would give me the power rule 3x cubed divided by the new power of 3. So essentially just x cubed. And then the antiderivative of cosine, so positive sine, and then plus the constant of integration. If you are to solve for the c, you need the value of an initial condition. This would be the solution to a first order. So that means you're starting with a first derivative, and then you're solving that by separating and integrating, and then finding the value of c. So here's a differential equation, also given us a specific point. So we separate the terms. So e to the 2x minus 3x followed by dx. And then we'll integrate each side. We'll get y equals e to the 2x divided by the natural log of e, which is 1, and then 2. So we could simplify that and just say e to the 2x over 2. Minus the power rule, so raise the power and divide by the new power, and then add c. So now we're going to substitute in the values of 1 for x and 1/2 for y. So 1/2 equals e squared over 2 minus 3 over 2 plus c, and then we solve for c. So if I add 3/2 to both sides, I'll get 2 equals e squared over 2 plus c. So then c will turn out to be 4 divided by e squared. So that gives us a particular solution. And the solution would be y equals 1/2 e to the 2x minus 3/2 x squared plus the constant 4 over e squared. we use the fundamental theorem also to solve our initial value question. Okay, if we integrate both sides, so it's already separated, and then if we take the integration, so this would be the integration of f prime of x, and the integration, well actually, it'd be better if we rewrote f prime as dy dx so that we could do the separation. So we'll have dy equals cos x squared dx, and then we'll integrate. And so we'll get y equals, now the cosine of x squared dx doesn't have an antiderivative. Okay, it's not cosine x, it's cosine x squared. And so we can't find the specific antiderivative, but we know that there's a plus c, and so the constant would be written this way. Right, the initial condition tells us that the c value is 5 when the x value is 3. And so 5 would be our initial condition, where the area starts accumulating at 3 to an unknown x. And then because we've used x as our upper bound of our the unknown bound, the unknown upper bound, you need to choose a different variable to finish writing your integral. You can't continue to use x, and I don't care what variable you use. I mean, you could have kept x squared as your variables here and said x squared dx, and then used t or a or some other variable, but your unknown bound should be a different variable than the variable that you are integrating with respect to. All right, so you'll work with a few of those sample problems. You shouldn't have probably any trouble with those. And then we will talk about U substitution together on Thursday.